Hello, I am Vladimir Petrov, and we are starting the cycle of lectures and seminars in the course of Basics of Nuclear Chemistry. And today will be the first lecture on this topic, and it will be introduction to the radioactivity and the applications of ionizing radiation and radiation technologies. So, we will start with the term radioactivity. What is it? In principle, it is a physical phenomenon that is defined as a property of a certain nucleus to spontaneously rearrange, transform its composition of and energetic level. And this phenomenon resulted in emitting of ionizing radiation and also in the changes of the chemical composition of the matter. And that is more important, or also important, that this process is a spontaneous process. That means that during this process the energy is released. But we will stop for the moment at this term and we will go back to the basics of chemistry and physics, and we will see what is the atom and where is the nucleus in general. So everything is consists from atoms, and atoms is very small particles around 10 to 10 meters in size, and inside the atom there is a very small but very heavy nucleus that consists of protons and neutrons. Together we call them nucleons as a part of the nucleus. And proton and neutrons, they have a mass that is around 1 atomic mass unit, and proton has charge +1, and neutrons don't have any charge. So around the nucleus there are electronic shells filled with electrons. Electron is a very small particles with the mass around 2000 times less than the mass of proton or neutron, and electron has a charge -1. Nucleus in general is very tiny particle, tiny fragment of atom. It is only 1/10,000th part in size of the atom, but the whole mass is located inside the nucleus. The number of protons defined the position of the element in periodic table of elements. As the mass of proton and mass of neutron is almost the same, we can say that the whole mass of the element or certain isotope of element is consists of number of protons plus number of neutrons. Again, number of protons tells us where the element is located inside the periodic table. And here you can see the comparison in masses of neutrons and protons. And you can see that the exact numbers 1836 and 39 for protons and neutrons respectively. And you see how small is the electron mass. And by definition, atomic mass unit, it is 1/12 of mass of the isotope of carbon 12, and there is this number in kilos for information. And as the number of protons defined as the position of the element and periodic table, and thus the chemical properties of the element, the number of neutrons define the total mass of the certain isotope or certain nuclide. There are isotopes for the elements, and the isotopes means that the certain element thus contains the certain number of protons, can have different number of neutrons. So the chemical property of this isotope or the same element will be the same, but their nuclear and some physical properties can be different. There is an example, the simplest example of the concept of isotopes for hydrogen. When there is no neutrons inside the nucleus, just one proton, we can call it protium. If we add one neutron, we now can say that we have deuterium, the heavy isotope of hydrogen. And if we add one more neutron, so two neutrons and one proton, then we call this isotope tritium. And for example, protium and deuterium, they are stable nuclides, so they are non-radioactive, but tritium is already a radioactive isotope of hydrogen. So we call the radioactive isotopes of elements radionuclides. But we cannot call the all radionuclides just isotopes, because there are stable isotopes, radioactive isotopes, but that is more important that isotopes, we can use the term isotopes only for a certain element. We can say that this is isotope of cesium or strontium, but we cannot say just isotopes, radioactive isotopes. Thus, it is important to use correctly the term radionuclide and isotopes. Don't mix them with each other. Nucleus, like an atom, like an orbital shells in atom, there is also energetic levels in nucleus. We know that when the electronic shell in atom is fully filled with the electrons, then we obtain the very inert elements. It is the noble gases. Thus, the completely filled electronic shell demonstrates the very high stability towards addition of any additional electron or towards losing of electrons. The same is for nucleus. If the energetic level in nucleus is filled completely with protons and neutrons, this nuclide, this nucleus, will be very stable. And the numbers of nucleons that can fill the different energetic level, these numbers are given in this scheme. And you can see them at 2, 8, 10, 20, and 30. And these numbers are called the magic numbers because nuclei with this number of protons or neutrons or their sum are very stable. And they are non-radioactive and very stable, etc. But again, in nucleus there is only protons and neutrons. Neutrons don't have any charge, but protons they have positive charge. They charge the same. Thus, there should be a repulsion between these particles. We know it from basic physics. But we know that protons and neutrons exist in nucleus together without any problems. But so, why it is so? In principle, there is not only electrostatic interaction between different particles, but when protons and neutrons are coming close to each other, sufficiently close to each other, then there is another force that is called nuclear interaction force that is much more stronger than any electrostatic interaction. We can estimate this difference in electrostatic interaction like around hundreds, thousand times nuclear interactions are stronger than any chemical interaction or means electrostatic interaction. And when we talk about nuclear interaction, then we say that mass, there is no mass conservation law, but there is energy conservation law. Because energy and mass, we can write this famous expression about the relationship between energy and mass, where energy is equal to mass multiplied by c squared, where c is the velocity of light. And it is interesting that if we take separated protons, neutrons, and electrons, calculate their mass, summarize these masses, then we obtain the larger value than the mass of an atom where all these particles are combined. And there is an example for oxygen 16. We can take mass of 8 protons, mass of 8 neutrons. We know this mass exactly, and mass of electrons also calculated to summarize, and then we obtain that this summarized mass of separated particles are larger than the mass of the atom of oxygen 16. That is determined experimentally by mass spectrometry, for example. And we can calculate the mass defect, and from this value of mass defect we can calculate, using this expression, the energy of nuclear interaction inside the nucleus of the atom of oxygen 16. And this number is equal to 127.5 mega electron volts. And if we divide it by the number of nucleons inside the nucleus, means the sum of protons and neutrons, we will obtain the number around 8 mega electron volts per nucleon. Is it big value or small value? For example, the energy of chemical bonds we can estimate in the range of few or maybe dozens of electron volts. And this is mega electron volts, means a million times larger than just electron volts. Again, we can say from this observation, from these calculations, that the energy of nuclear interactions something like 100,000 times stronger than any chemical interactions. If we will see how the average binding energy in nucleus is changing with the mass of nucleus, we will obtain this curve from which we can see that the energy is increasing when we go from the very light atoms to the heavier one. That means that it is efficient process of combining of small nucleus resulting in heavier nucleus. And this process, of course, requires some additional energy from outside, but this energy is required because nucleus, they have this positive charge, and when we try to make them very close to each other, then we have this repulsion forces. But if we push them with very high energy, then they can interact with each other, producing very large energy that is much larger than the energy that we put on them. And thus, these processes of interaction of very light nucleus can produce very large energy, and that is called fusion nuclear reactions or thermonuclear fusion reactors. And these processes occurred in the stars. So all the elements of all the elements that we observe, they are synthesized inside the stars. And after some certain point on this curve that is located around the iron, there is a decrease in the average binding energy. That means that for very heavy elements like uranium, plutonium, and others, there can be very favorable to split onto lighter atoms which have higher energy of the binding inside the nucleus. And this process called fission, when we split atom, and this process produces also a large amount of energy. So at the moment, all the nuclear reactors that we have in operation, they are working with the fission of the heavy elements, and there is a project, the huge international project, to develop the reactor that will work using the fusion reactors, because they are much more energetically efficient. But how the radioactivity was discovered, and is it a handmade process, artificial process, or not? Actually, radioactivity was always. It exists since the beginning of the existence of our universe, but it was discovered only 125 years ago in 1896 by Henri Becquerel. Henri Becquerel was studying the luminescence of uranium salt. It was known at that time already that if we irradiate uranium-6 salts with UV light or just by sunlight, it emits very nice green color. So this process called luminescence. But it was also observed that during this luminescence process, uranium emits also some unknown rays that can penetrate through the paper and thus can have an effect on photographical plate. And at that time it was assumed or suggested that these unknown rays they arise also when uranium is irradiated by sunlight. So there were a lot of different experiments with uranium salts, depending on the composition of uranium salts, on the intensity of the sunlight, on action of pressure and many other parameters, temperature, for example. And the observation was that independent on these parameters, these unknown rays are emitted. It was the first observation. And the second observation was done, we can say it by chance, but it was possible only if you are working a lot with the same object for decades and you have an idea what you can do also with this object. And so in 1896 there was a very bad weather for a couple of weeks, and thus it was not possible for Henri Becquerel to irradiate uranium salts with the sunlight, because it was cloudy, so he just put the uranium salts together with photographic plate inserted in the thick layer of paper in the table and leave it for several days. And as far as there were no sunlight still, he decided just to check if something happened with the photographic plate. And he observed that even without the sunlight, the uranium salt still emits these unknown rays that had an effect on the photographic plate. So with sunlight and without sunlight, it was the same result. Thus, Henri Becquerel suggested that it is an internal property of the uranium to emit these unknown rays. So we don't need any other effect on uranium salts to that uranium starts to emit these unknown rays. Since this discovery, another scientist, first of all Marie and Pierre Curie, decided to investigate this unique property of uranium salts, uranium minerals, and they observed that in some minerals these unknown rays are emitted even with higher intensity than for pure uranium. And this got them an idea that there should be some other elements with the similar properties to uranium, and these elements emit unknown rays even with higher intensity than uranium. Thus, with this idea, they worked with a huge amount of uranium ore, and they discovered the unknown, at that time unknown elements, radium and polonium. And the term radioactivity was introduced by Marie Curie. And so radium is called radium because it means that it is the element that irradiates some rays unknown at that time. And polonium is called polonium in honor to the fatherland of the Marie Curie. Marie Curie was a very impressive woman because she was not only the great scientist with 2 Nobel Prizes, professor of the university, but she also went to the front line during the war, and she worked there together with her daughter as a medical assistant, as a driver and mechanic. So it is a very great example of humanity in one person. And the discovery of radioactivity and the ionizing radiation allowed to discover many other things that we know together, that is stated even in the school textbooks. But all these discoveries, all these investigations become possible only with the use of the radioactive materials and ionizing radiation. So it is the classical example of use of alpha particles to discover the structure of nature, the structure of atoms. It was experiments of Rutherford, where he, with his assistants, observed the scattering of alpha particles that were going through the very thin gold foil. And for many alpha particles, it was very small scattering angle, so they went directly through the gold foil without any scattering. But in some very rare events, alpha particles scattered to the very large angles. And in some cases, they even backscattered from the gold foil. And the only explanation of this observation was that there is a very small but very heavy particle inside the gold foil that is positively charged, that contains all the mass of the atom, And from these observations, Rutherford proposed the model of the atom that we use today. Where the nucleus, very small fragment of an atom, contains all the mass, and there are very large electronic shells around this nucleus. And and again, it was possible to make this observation only using the alpha particles, only after the discovery of radioactivity and after understanding what is the alpha particle. There is quite an intensive history of using of radioactivity or radioactive materials, ionizing radiation, to understand the nature of atoms, the nature of nucleus. In 1902, the Rutherford and Soddy, they observed the generation of radioactive emanation from radium. It was a very simple observation, but again, only people who work very hardly on the topic and who understand what they can observe and what they cannot observe can do these conclusions from even simple observations. So they measured the activity of radium samples and the detector and radium salt of radium samples. There was a difference between detector and the sample, and when they opened the window just to have a fresh air, they observed that the intensity, the activity of the measured activity was decreased. So why the only explanation was that there is a radioactive gas that is accumulated that is released and accumulated from radium salt, and when the window is open, this gas simply goes out, and thus the activity is decreasing. And this simple observation leads to a discovery of the concept of the radioactive transformation of the elements. By 1910, they have already discovered 40 radionuclides, natural radionuclides, and it was again the idea where to put all these radionuclides. What are their chemical properties? Are they different from the properties of the already known elements, or are they different? And Soddy introduced the concept of the isotopes, and with the discovery of the mass spectrograph, it was possible to show that the same elements have different isotopes. And this idea, the concept of isotope, was proved. Later, so like 20 years later, neutron was discovered in different observation. Bolte and Beckler, they observed, they discovered the neutral irradiation, and Chadwick discovered this particle as a neutron and called it neutron. And later, in 1934, it was a great discovery of the Irene and Frederick Joliot-Curie, where they produced the artificial radioactivity. Before that, there were only natural radionuclides, and it seemed that it is impossible to produce, to make artificial radionuclide. But in 1934, by the use of alpha particles released from the natural radionuclide, Frederick and Irene Joliot-Curie produced an artificial radionuclide by bombarding aluminium with the alpha particles. Then, in the same year, Fermi observed the energy released by irradiation of uranium by neutrons. And later, in 1938, Otto Gahn and Strassmann proved that the observed energy released is associated to the splitting of uranium nucleus, to the fission of uranium. It was not easy to understand at that time what is happening, because all the known types of radioactive decay said that if you have radioactive decay, you can move, or you are changing your nucleus only by very small difference in charge, -1, +1, maybe -2 in the case of alpha particles. So you always produce the elements that are located near the parental radionuclide, the initial radionuclide. But in the case of uranium fission, they observed, Otto Gahn and Strassmann, that, and Lisa Meitner, that there is an elements that are far away from the uranium. They are located in the middle of the periodic table, while uranium is located at the end of the periodic table. And it was very difficult to understand what is happening, and many people didn't believe in the possibility of such splitting of the nucleus, but it was proved. And later, in 1940, Flerov and Petrov discovered the spontaneous fission of uranium-235. And already after 2-3 years, this fundamental discovery resulted in the construction of the nuclear reactor. So it's application of fundamental discovery to the industrial field. It was very fast, and already in 1945 the first atomic bomb was tested. So we can see that the invention of the atomic bomb took only 5 years from the discovery of spontaneous fission of uranium-235. So it is very intensive field of the research, of the technology development. But it is interesting that already in 1912 Vladimir Vernadsky said that, and he realized that the energy that is located inside the atomic nucleus is so big that man can use it as a source of energy. But the question will a man be able to use it for good or for self-destruction? And it was very words that we're looking in the future. So after 20 years or 30 years, the atomic bomb was discovered, and only after several years the peaceful use of energy started, when the atomic nuclear power plants started to operate to produce electricity for cities, for just citizens. So peaceful use of nuclear energy. And today the most known, the well-known application of the nuclear energy, or the ionizing radiation, it is of course nuclear power plants, which can produce the energy, the electricity and thermal energy without emissions of CO2. Nuclear power plants compete very hardly with the wind turbines. Another application of ionizing radiation in modern world, it is the nuclear medicine. It is either diagnostics or therapy, and we can use radiopharmaceuticals. That means that it is medicine that contains inside it the radionuclides, or we can use accelerator therapy. So it is the radiation techniques that use the special equipment that accelerate the alpha particles or other nucleus, like nucleus of carbon 12 or nitrogen, and these accelerated highly charged particles can have therapeutic effects for some diseases. Another maybe not very known application or direct contributions of radiation technologies, it is waste treatment and some others that I will tell you. So the waste treatment means not only the nuclear waste production, but also decrease in the of content of oxides of nitrogen and sulfur in the gases, in the gas streams that are released from coal power plants and other facilities, or we can use irradiation for cleaning the tap water to sterilize the aqueous waste streams. Also, it is the removal again of oxides of nitrogen and sulfur in oil and gas production power plants, not power plants but just plants, the oil and natural gas are treated to produce liquid hydrocarbons. It is irradiation and disintegration of the solid medical waste, for example, and some application for, of course, nuclear waste. And there is a pest control that is very interesting application of ionizing radiation. So for removal of oxides of nitrogen and sulfur, we can use special radiation techniques that produce a lot of radicals inside the gas stream, and thus these radicals attack the nitrogen and sulfur. These radicals oxidize nitrogen and sulfur to higher oxides, and then these higher oxides of nitrogen and sulfur are removed by absorbing in water or in solutions of sodium hydroxide or other alkalis. Thus, these gases can be removed from the waste gas streams quite efficiently. Another application is the treatment of nuclear waste with the accelerated driving system. It is very unique technology that is still under development, but with these techniques we can decrease the number of radioactive waste by transmutation of the long-lived radionuclides and for transformation them to either short-lived radionuclides or even to stable elements. The pest control that I told you before is used for control of some infections that are transported by insects. And what is the scheme of the process? Part of the male persons of insects are taken from the nature, then they are irradiated by ionizing radiation, thus they became sterile, and then these sterile insects are going back to the nature. In nature, they try to make a population, but as far as they serial, they cannot do it. And thus, the whole population of the insects is decreasing, and the spread of the infection is also decreasing. Indirect contribution of radiation techniques is in decreasing of use of organic solvents and other chemicals in production of polymers, for example, and semiconductors. And thus, with use of radiation techniques, we can decrease the use of hazardous organic solvents, organic compounds, and other chemicals. And this is examples of cable production and semiconductor production without use of special chemical components that generally uses in these productions. And another important indirect impact of radiation technologies is their impact on society. Radiation technologies require the highly qualified specialists. Thus, we need to increase the quality of the higher education, and thus the students that want to go to these universities, institutes, to learn more about radiation technologies, they need a more intense school program. And this leads to a need to improve, to develop also education in schools, and to spread the information about radiation techniques, etc. Thus, all this require the improvement in education and science, in technologies, because for radiation technologies we need quite unique equipment, technologies, etc. And as a general impact on society is the improving the quality of life, because the more educated the people, the more they concern about the environment, about the society, about each other. Thus, this indirect impact of radiation technologies are very important. And another impact, maybe we can say that it is direct impact, it is impact of nuclear weapon investigations. Nuclear weapon is very efficient weapon, but many people scared of it because of its efficiency, let's say. But instead of all the negative sides of the nuclear weapon, we can say, scientists say that the end of 20th century and our 21st century, the beginning of it, is the one of the most peaceful period in the whole history of the humankind. Because if one side will use the nuclear weapon, then there will be no chance to survive for humankind. Thus, there is a special website, the Bulletin of the Atomic Scientist. They're the specialists in nuclear science, in social science. They publish their reports, and they also make a conclusion about the time before the so-called nuclear midnight. So midnight means that some of the country will use the nuclear weapon against the other country. and the time before the midnight represents on how far we from this global conflict. And to end this introductory lecture, I would like to say that everything, and of course the radiation technologies and radioactive materials, must be used wisely. There is a picture from internet where one man was complaining that gun sellers are also responsible for the crimes, and another guy stood there and saying, okay, then spoons made me fat. That means that it's not the fault of the instrument that something went wrong, but it is the fault of the person who uses this instrument. Even with such common things like cooking salt or just pure water, someone can use it wrongly, and there is reported lethal accidents with the use of these quite simple chemicals that we use every day, when people died after consuming very high amounts of salt or just water. Thus, again, everything, even water, must be used wisely. That is all for today. Thank you for your attention, and we will meet later.